So how do we teach multiplication and division for understanding? Now, I pose this question because I had a friend who got a hold of me because she was concerned that her daughter, who's in fourth grade, was struggling with division. It took me a little bit to kind of dig into it, but basically she was concerned because her daughter didn't know the standard algorithm for long division. My first response once I figured that out was, okay, stop for a second, because the standard algorithm is something that kids should be getting in sixth grade for division, fifth grade for multiplication. So I told her, don't freak out, it's gonna come, but she was concerned because that wasn't the way it was being taught. Well, we didn't learn that way. The way that we all learned was just the standard algorithm. So she was like, why? She's not learning division. But guess what? Her daughter is learning division and multiplication, but in a way that's developing her understanding and not just the algorithm. I'm Christina Tondevold, and I hope that you'll stick around as I talk about how do we teach multiplication and division with understanding so that kids can actually do the algorithms but understand them. If you were anything like me, I could perform the algorithms, but I really had no sense of what I was doing. It was hard for me to even know if my answer was correct. I could perform an algorithm, but I had no sense of numbers. So let's dig in to how we teach multiplication, and then we're going to dig into how to teach division, all in a way that leads towards understanding the standard algorithm, but builds kids' number sense and place value sense along the way. Okay, so let's start off with multiplication and the traditional way that we all learned this. So let's do 24 times 17. All right, we learned you do the 7 times the 4, that's 28, and you have to put the 8 here and you carry the 2. And then we do 7 times 2 is 14, and then add the flying 2 up there. So now we should have 16. And then we go over to the 1, and now we do the 1 times the 4. And half the kids want to put the 4 here, right? But our teachers will teach us, no, you just move the 4 over here because it has to be underneath the 1. That's where you start. And then we go to the 1 times the 2, and that's 2. But half the kids will think, oh, I've got to do something with that flying 2 up there, right? But if they do it correctly, they will end up with this. The hard part is, a lot of our kids can do this, but they do it with no real understanding of what they're doing. Just even like this with putting the 4 over to the side. Why do we do that? Most of us just learn that's what you do, okay? But let's take a look at some ways that are being taught now and that we're trying to develop in kids to help kids understand this algorithm when they get there. Now, one of the ways is to think about it as groups of. That basically we need 24 groups of 17. That's one of the ways that kids think about multiplication, is that means 24 groups of 17. And so I need to build 24 groups of 17 basically. And so some kids, when we're starting with young kids, and let's just say it was 4 groups of 17, a lot of times they would start out with just repeated addition. I could do 17 plus 17 plus 17 plus 17. That becomes really inefficient as we start moving into big amounts like 24 groups of 17. But kids might know something like 10 groups of 17 is 170. Well, then if 10 groups is 170, 20 groups of 17 is going to be double that, which is 340. Well, I've got my 20 groups, but I need 4 groups. And one of the things that kids might know is that 2 groups, I'm just going to abbreviate, of 17 is 34. So 4 groups of 17 is going to be 68. And so to get 24 groups, I just need the 20 groups and the 4 groups, and I have to add those together. Now, this seems like a complicated mess here, and it seems really lengthy, right? It seems like a lot more steps in the algorithm, but we're helping again to build an understanding of what 24 groups of 17 is. Now I'm going to pause this for a moment, or I want you to pause it because I'm going to move on, but I want you to look at that. And when we've got 20 groups of 17 and 4 groups of 17 gives us 68, and then we've got the 340. Do you see that anywhere over here? Now I'll tell you, it's a little hidden, but it's there, and I want you to pause and think about where it is. Why does that 68 show up? Where does that 68 come from? Okay, and then I'm going to show another way, another strategy here in a moment that might connect a little bit clearer to that algorithm there. Okay, so another way that before kids learn the algorithm, that we want them to understand multiplication is connected to area. When you're solving area, you're using multiplication, and vice versa. When you're thinking about multiplication, it can be the length and width, or rows and columns, however you want to approach it. Now, there's a big debate about which one should be rows, which one should be columns. I'm not going to handle that in this one, so if I do it backwards than the way you think about it, please forgive me. But basically, you are wanting kids to see this as 17 by 24. However you want to write it, you might have the 24 on the other side. Now, I don't know right off the top of my head what 17 times 24 is, but I can slice this area model into pieces that are more friendly. And this again may connect back to one of the ones we just did, right? And a way that kids will often slice these is thinking about 17 is really 10 and 7. That would be that whole length down that side. This side could be seen as 20 and a 4. And then now I've got 4 areas to figure out, but those areas are a whole lot easier for me to figure out. I know what 20 times 10 is. That's really quick. A 20 by 10 rectangle, I know the area of that rectangle. A 4 by 10 right here is going to be 40. A 20 by 7 is going to be 140. And then the last one of 4 by 7 is going to be 28. Whoop. There we go. And then I've got to put those together, which a lot of people think, well, now I've got to do a lot of addition. Well, guess what? Our kids need practice in addition, even when they're doing multiplication. They still need some practice in that. So this gives them another opportunity to become a little bit more fluent and flexible with their addition. And there's lots of ways kids could add this up. I'm not actually going to show a way to add it because I want you to think for a moment, pause the video, and think about how does that strategy connect over to this? Do you see any of those parts in one of those strategies? And can you connect it to the other strategy? Can you see in the area model how it connects to that traditional algorithm? If you don't want to know yet, pause the video because I'm going to show you. Okay? So if we go across here, whole way here and add up this way. This gives me 240. This row gives me 168. If we look over here, here's my 168 right here. I'm going to put a little equal sign because we're going to talk about where that came from. And then this little 24, guess what? It's not a 24. The way I learned it was just a 24. We just left that space empty there. But really, right there is a 0. It's not just 24 because of how this is connected. So that row is really 10 times 24. The 10 here and then 24 all the way across there. Okay. We have 7 by 24. And if we think back to our algorithm, the way that we all learned it back when we were in school, we did 7 times 4, but then we did 7 times 2. That's really not a 2. It's a 20. It's 7 times 4, and then we did 7 times 20. And that together makes 7 times 24, which is 168. So the strategies that kids are developing before they learn that traditional algorithm are going to lead into not only being able to do the algorithm, but understand that algorithm. So yes, eventually we want kids to understand and be able to do that algorithm, but we want them to do it and understand it along the way, not just compute and get an answer. Because too often we see kids who will compute, they'll do the steps, and maybe they make an error along the way, like having the 24 over here instead of moving it over, and they don't even realize that they're off. They don't realize that 180 something, what would that be, 192 is way too small of an answer. But they performed the algorithm. Yes, they performed it incorrectly, but performing it incorrectly is due to them really not understanding what's happening in the algorithm. All right, so let's move on. And these are not the only strategies. I only showed a couple because this video would be super long if I showed everything. But I just wanted to show a few strategies that students should be developing in order to help them understand the algorithm. So let's move into division. Okay, so let's say we have 4,812 divided by 4. And yes, I picked this on purpose, and we'll look at why the long division algorithm doesn't build understanding here. Okay, I'm going to talk about the way that we would do this. Normally, we would learn that we look at 4 goes into 4. How many times does 4 go into 4? And kids would say 1, and we do 1 times 4, and that's 4. We get 0, and then we have to bring down the 8. How many times does 4 go into 8? Would give me 2. 2 times 4 is 8. 0, and then I'm going to bring down the 1. And then we can say 4 goes into 1, and they say it doesn't. And half the kids forget to put the 0 up there. And they just bring down the 2, and they say, oh, 4 goes into 12 3 times. And they say it's 123. They did the algorithm, and again, yes, they did it incorrectly, but their incorrect use of the standard algorithm is often based because they don't understand what they are doing. So instead, if we can build their understanding of division, when they get to a problem like this, when they start doing the traditional algorithm, they realize and can look at that and say, my answer should be in the thousands. But so many of our students, if they move straight to the algorithm, they're not building an understanding and building place value and number sense along the way. So let's look at some strategies that kids might develop around division before they get to the algorithm. Now I'm going to put in that correct version here because that's bugging me. All right. So one of the ways that kids will see this is that they will want to break it up by the amounts that make sense to them. So kids will see that, wow, there's a 4 and an 8, and they make some connections like 4 and 4, those work nicely together, and 4 and 8. So they'll want to use the things they know about numbers, but we want to help them develop the understanding that that 4 in the 4,000 right here is not just a 4. It is 4,000, right? So let's set this up here. 4,812 divided by 4. We can set it up the exact same way even. But when I'm going 4 into 4, that's really 4,000. How many times does 4 go into 4,000? Hang on one second here. I'm just going to move this to give me a little bit of room. All right, so the 4 goes into 4,000 1,000 times. And 1,000 times 4 is 4,000. And then when I subtract, I'm not just bringing down the 8. I'm bringing down all 812. There's still 812. And I need to figure out how many times does 4 go into 812. Well, I know that there's an 800 there, and 4 will go into 800 200 times. So that is 800, and then I just have 12. How many times will 4 go into 12? 3. So my answer is 1,203. Now, some of you may notate that differently. I've seen ones where, let me get a different color here just to notate it. They may put it off to the side here. Let me finish that out. I didn't finish my minus 12 gives me 0. Okay. It's the same idea. We're wanting kids to see it as a whole. It's not just how many times does 4 go into 4, 4 go into 8. It's how many times does 4 go into 4,812. That's the picture. And guess what? If they develop that understanding, they'll get to a point where on these quote unquote easy ones, I'm totally using air quotes right there, they will be able to do that in their head. They will think, okay, I've got 4,812 and I'm dividing it by 4. Well, that 4,812, I can divide each one of those by 4. Whoops, I just realized I didn't have another 0 there. There we go. All right, so that gives me 1,203. And that's my answer, 1,203. Now, yes, I realize that works nicely on a nice problem like this, both of those strategies, but that's the idea. We want to develop that strategy on easy problems so that even when they get to ones that are more difficult, they're using that same idea. Okay, so let's try 9,876 divided by 7. Now, I totally made that up, and we'll just see how it comes out. I don't even know if it's going to go evenly here. All right, so my first thought here is I need to do 7 into that 9, right? That's the traditional algorithm way. But if we're building understanding, that 9 is really 9,000. So if I have 1,000, I know that 1,000 times 7 would give me 7,000. So I'm left with 2,876. Now, what I know about numbers is that I know that 4 works nicely with an 8, with the 7 there to give me 28, but it's not 28, it's 2,800. And so I'm not really just putting a 4, that 4 is really 400 times 7 gives me 2,800. And then when I subtract, I've got 76 left. Oh, that works nice. So I've got 10 would give me 70, and then I'm left with a remainder of 6. So my answer is 1,410 with a remainder of 6. Now, if you're working with fractions, you can have them write that as 6/7, right? But that's the idea, is that we're building their understanding so that when they come over here and they do that with the traditional algorithm, 9, 8, 7, 6. And what they normally do is 7 into 9 would be 1, right? And they have 7, 2, bring down the 8, and it's a 4. But again, that 7 here is not really a 7. It's 7,000, right? That connects there. This 28 that's left over is 2,800 that's left. And so when I put a 4 up there to multiply it by, I'm not just getting 28 here. It really does mean 2,800. And the reason we leave that off, why the traditional algorithm became that way, is because it took time. It took time to write those extra zeros in there. It takes time to subtract all the way down. But when you lessen the time, you lessen the understanding, you lessen the place value, and you lessen the number sense that they are building. So we're getting more efficiency, and it takes less space to write it. But what we're losing is place value understanding and number sense and a reasoning of whether or not their answer is even reasonable, right? We get so many kids here. So when they bring this down here and they get 7 and 1, so many of our kids will even stop here and be like, oh, that's 0. And they'll leave it as 141 and not even think about it, right? But if I'm going completely through this, right, I'd have to put a 0 here, times by 0, and then I would have a remainder of 6. So, again, the algorithm is not bad, but it's not the first thing we should be teaching kids. We want to develop their place value. We want to develop their number sense through these strategies so that when they get to the algorithm, they can make sense. They can make connections here between what's happening. That 7 is really a 7D. That 28 is really 2,800, and so on. So yes, doing the standard algorithm that we kind of all grew up learning is really fast and it's efficient, but so many students don't really understand what's happening and will end up with incorrect answers and not even realize it because they don't have a sense of numbers. So I hope that through those strategies that I just showed you, it helped you see how we are moving towards the algorithm, but along the way, we are building their sense of multiplication and division along with place value and just general number sense in order to help our students build their math mind and not just become a calculator, right? We want kids to be thinkers, not just calculators. So I hope that this has helped you build your math mind so that you can build the math minds of your students. Have a great day.